Okay, I'm just gonna get started then. So this, I guess, is like a kind of progress update of sorts for the stuff I've been doing over the last 4 or 5 months now. And it started off working on temporal memory, getting acquainted with the algorithm, reproducing it, potentially trying to make it faster. And this was kind of like a sub-project of sorts to be done with temporal memory. It was sample invariant object recognition. So I'll try to go through this quickly. There's quite a bit to go through. I'll go over the problem that I was trying to address, the kind of data that I was working with, the algorithm I was using, the results, and then potentially where to move from there. Okay, so the main question I guess we want to ask is, can I use a single sheet of temporal memory, so exactly one column, one level of the hierarchy, and just one layer for some kind of sample invariant object recognition? And if I phrase that differently, I can ask the question, if I revisit part of an object I've never seen before, can I identify what object it is, no matter where I sample?
And here, when you say one column, you mean one cortical column?
Yes, one cortical column.
When you say one layer, are you using any concept of locations in there?
No. Well, there's no layer dedicated for locations.
But there's a location signal.
Yeah.
Okay.
Similar, we don't have a grid cell layer.
Got it.
Yeah.
All right, sort of like we did columns.
Exactly.
Okay.
Yeah.
But so that means one layer means there's no input and output.
Well, one layer means there is an input and there's no output going to another layer.
Yeah.
There's no pooling either, because there's no object ID layer of any sort.
And this is really just to focus on just answering this little question for a while before we put it into a fuller, bigger system.
Well, how does it differ than the columns you get with them?
I haven't gone before. So this is the idea of like this continuous sheet. And,
Yeah.
looking at the
And we're not
thresholds.
changing orientation. No.
Not yet.
Okay, great.
So basically, can I disambiguate between multiple objects that I've trained on while observing some kind of features at locations along the object surface? And the question is, why is this important? And at the risk of grossly oversimplifying what deep learning is doing in this field, I'd state that they need to ingest a lot of information about any kind of 3D object in order to potentially disambiguate between multiple objects or recognize an object despite occlusions. And we saw in Curran's example, the vector neurons kind of. Okay, so the kind of data that I'm working with is the YCV mesh data set. And basically, you can think of it as every object is its own individual point cloud. And the point clouds kind of range between anywhere from 7,000 to 12,000 points, describing that object's morphology. So it's quite a reasonable number of points. So the feature that we're looking at is basically the Gaussian curvature value for every single one of these points. You can think of this as like the proximal input to temporal memory. And the context, which we can think of as like the basal input, is a location in a fixed object-centric reference frame. This reference frame doesn't change for any of the objects. Okay, so just want to quickly address this. Like, why are we using point clouds? Why not anything a little bit more complicated? And the reason for that is it's quite a simple data format for quick and easy prototyping, but there are plenty of caveats. The first is that preprocessing is quite expensive just because there's thousands of data points. And in my case, since I'm using temporal memory, converting between point clouds to SDRs is quite tricky. You're trying to create this kind of continuous set of SDRs where there's a continuous overlap between points from inherently discontinuous point cloud points.
Why do you have to process all the data points? The whole point is to do a subsampling of the data points and see if you can recognize it with a different subsample.
Right, but in order to, you're right. I'm only going to pick a part of it, but I still need to pre-process everything.
You did it, all right, but that wouldn't be an inherent part of the problem. That's just the way you did it.
Yeah. For testing, for instance, I would need to pre-process everything because I'm randomly picking.
Yeah, you're randomly picking ones to learn on, you're randomly picking ones to infer on, right?
Yeah.
So you wouldn't need all 7,000 points. You would just use a few of them.
Not at any given one time, but yeah.
Yeah.
The other challenge is yielding some kind of reasonable overlap between neighboring points, whether that's in the coordinates, whether that's in the curvatures. And this kind of process is really done through some kind of trial and error. And there's also the problem of precision. The point clouds are real valued, but SDRs are quite discrete. So everything needs to basically be casted as integers before I even proceed. So there's a little bit of information that's being lost. Okay. I'm going to do a very, very high level overview of this, simply because I don't want to spend too much time on this, but this is kind of like the strategy for encoding any of the points, the coordinates into SDRs. So the first step would basically be to scale all the coordinates for a given object. I think this is like a pair of binoculars or a Lego piece. I can't even tell.
It's not binoculars. Not binoculars?
Yeah.
Okay.
I don't know what it is, but either way, for all the objects that you're using, you're going to scale the coordinates to some kind of similar range, and you're going to convert all the floating point values to integers. And if you guys can see the purple point right over here, this is like a sample point that I want to convert into an SDR. And how I would do so is define some kind of fixed sphere around that point, and then basically try to compute all the neighbors in that sphere. And when I'm computing the SDR, I'm randomly but deterministically picking some of those pink neighbors that you see, and I'm hashing their values to some buckets or indices in some SDR. And I set those buckets as on, and I set the rest as off. So
This is similar to the coordinate.
this is the coordinate code, yeah. Just a visual representation of the coordinate code.
This is a good explanation.
But yeah, you would think of doing this for basically all the points that I have in my point cloud to get individual SDRs for all.
Does that then, so just for the kind of metric of nearness then of nearby points, is it kind of then a discrete effect as you get within that cloud, or do you then almost have more of kind of a continuous effect if you were to sample a random point depending on its nearness to another point? Is there a gradual increase in the overlap of their SDRs?
Yeah, so nearness is defined by whatever's in the sphere or not. So
it's more of a binary effect.
Yeah, but as you move that point, like I guess if you move that sphere down by picking different points at the center of that sphere, you do still get that gradual overlap between neighbors that you're moving between. If that makes sense. So even though it is binary, like whether I'm in the sphere or I'm not in the sphere, you do still get that gradual overlap if you move that sphere down.
Through the effect of multiple spheres, essentially.
Yeah.
Okay.
So that was for coordinates. You can do the exact same thing for curvatures. You would just scale all your curvature values to some same range, and you would follow the same neighborhood calculation and hashing procedure.
Sorry, so for the location, does that mean you're only storing like local location? So you wouldn't tell for the small cloud of points that you're hashing, you get some similarity for those, but not for slightly more distant points?
Yes, you wouldn't get similarity for more distant points. Yeah. But the coordinate encoder obeys this very simple principle, and that is if I have this sphere right here and I pick an even larger sphere, all the points contained in the larger sphere should be in this smaller sphere. When I've hashed into an SDR, there should be overlap. That's just a simple principle that you can test this by. So yeah, you can do the same thing for curvatures, but there's an inherent problem with the way we're doing this, and that's just there's too many points. A full point cloud, maybe like 10,000 points, it takes about 6 minutes just to process with a single sheet of temporal memory. So the whole idea here is, can we reduce the number of training points that we have? And one very quick and dirty solution is just kind of group the coordinates and the curvature into some kind of clusters. And I pick basically the approximate mean of every single cluster. In other words, I'm kind of yielding a finite set of the most commonly occurring features and locations. And I would only use those points to train. In other words, if I have a 10,000 point cloud, I'm just reducing it to n points for training, where n is the number of clusters that I've generated through my basically k-means method. So this is just a simple visualization of what this clustering even looks like. If I cluster by locations, basically clustering groups, the clusters are grouped by similar coordinates, you would get this center image here. See if I can, and just by looking at it, you can tell like the purple points, which are the training points, it's kind of uniformly distributed along the object surface, and that's exactly what we want, right? If I was only clustering by locations, that is something I would see. And if I was only clustering by the curvatures, this is something I would see, where I'm only going to pick the most commonly occurring curvatures in my point cloud. But there's a problem to both of those methods. And the problem is that in the first case, there's no guarantee in the overlap in the curvature SDRs if I'm only looking at locations, and vice versa. If I was only clustering by the curvatures, there's no guaranteeing the overlap for the location SDRs. So a reasonable middle ground that I found worked well is to do both. And that's the image that you guys see here all the way on the left. And that's basically just it's clustering by both. And there's some guarantee of overlap for both locations and curvatures.
But when you cluster by location, how do you make sure that they still end up on the surface of the object, the centers of the clusters?
So when I'm picking the approximate mean of each cluster, that point exists in the point cloud. So you're picking basically the point in the point cloud that's closest to whatever computed mean of each cluster is. So there's always a guarantee that all the cluster points are on the surface of the object.
Okay.
Jeff, you had a question?
I was just trying to, you're training sort of by, now you've got this set of points that you're going to train on, and you're just going to train them individually, right? Whereas if I was touching this object, for example, with a finger, I would be moving continuously along the surface. That would be a much better learning strategy. And it just strikes me that would be an important point of keeping, I mean, you would have sort of largely, it seems like that would make a difference. I'm having trouble expressing it. Is that a concern here at all? Or I mean, because you're just like, basically, this would be like, I'm just touching my finger randomly at different points around the object, as opposed to running my finger over the object, which seems to me, if we're trying to learn continuous representations using temporal memory, you would want to do it that way.
Yeah. That's absolutely right. I mean, like I could have done it that way. This was just easier, I guess, to experiment with. That would probably be a next step.
Well, I don't know what kind of results you're going to get, but if you're not going to get good results, then the first thing I say, well, that's not how I would have learned, right? In some sense, you almost guarantee the continuity if you move your sensor continuously along the surface.
Yeah.
Whether it's eyes or fingers, I don't know. So, all right, just bear that in mind as we get to the results.
In that thought experiment that you posed, I would technically the best learning strategy for, I don't know, learning what this model here is not only do I need to move in a continuous fashion with my finger, but I'd also need to experience all the curvatures, the most commonly occurring curvatures on this object, such that if I touched a different point that I've never touched before, I know exactly what this object is.
Well, you would, you might not know exactly what it is because it depends on where you had touched it, right? I mean, you might only touch the front side and then now you're touching the back side. So just be careful. Okay, it's going to taint when I look at your results, I'm going to have to keep that in mind. Like, hey, maybe this strategy of learning isn't the right one. Because if I think about how to create this sort of continuous, you want to, in some sense, create a continuous representation of the locations and curvatures. And that seems inherently the way you're going to do that is going to be important to keep in mind that you're doing this continuously. I can give some examples why doing it jumping around would not work.
Okay. So this is just a bit of, I guess, data about the data. So the curvatures that I'm using, the SDRs, are about 1,000 bits and about 11 bits are on. The coordinates, which is my basal input, and my apical input, which is the random but deterministic object ID for every single object. They're both about 2,000 bits and 30 bits are on.
So you're doing real representations here.
Yeah.
Where I would imagine if I think of curvature as the feature in some sense, like that's the output of the spatial pooler, it's not sparse like that. It's much denser SDR. Just bearing that in mind.
Yeah. The reason it had to be this sparse was because I was scaling the curvature values, the raw curvature values, into the exact same range as my coordinates so that the clustering would work.
Okay.
And that kind of affected how the resolution
that's another thing I'm going to put in the back of my mind, like, well, that's not quite right.
Yeah.
When we first did the temporal pooler, in fact, when we always had these fairly sparse outputs of the spatial pooler, but we know biologically that's not right. If you think about the mini clusters, it can work, but it's not that sparse.
Usually it's 20 to 30 synapses, right?
I'm just saying we would say, oh, we have 2,000 mini columns of which, I don't know, but in reality,
It's 40 on at a time.
Yeah, reality, it's more like if you look at the distribution of like V1 orientation columns, it's much less, it's much less sparse. But just keep going.
Okay. So yeah, I mean, there's about 1,024 mini columns here, and there's about 5 cells per column. And the activation threshold is 8. Jump into the algorithm. The algorithm is very, very straightforward. The biggest challenge in this whole sub-project was, I guess, getting the data correct. But the algorithm is that for every single object that I'm looking at, and for all the coordinates and the curvatures that I've considered in my clusters, I would pass in the curvatures as proximal input, the coordinates as basal input, and the apical input gets the deterministic object ID. And during training, I'm storing the winner cells for each observation as I'm iterating through.
I mean, in terms of the
Yeah,
numbers.
well, we didn't have the apical.
Oh,
I
April.
think it's maybe closer to the columns paper. The
Oh,
coordinates coming in and then the
Yeah, but in
object
terms of the
ID.
numbers and.
Numbers are very similar.
Yeah.
It's a little smaller because he was running into speed issues. But,
You're right, it's close to
Yeah.
columns, but I'm thinking like, oh, these are the kind of numbers we had.
yeah.
But in the columns one, there's that explicit object ID declarator that feeds back the.
Correct.
Okay,
Yeah.
so true. So this is like an approximation.
Well-
There's no pooling, which means I'm manually picking that.
Yeah.
Okay, inference is pretty much the exact same thing. I pass in the curvatures as the proximal input and the coordinates as the basal input. And the only thing is I'm withholding the object ID during testing. And the testing set notably could be either one of two things. It could be a uniformly sampled subset of the remaining point cloud, or it could be an occluded subset of the object. And I'll show cases where both work. But the goal here is that during testing, I want to store the predicted active cells. And after I iterate through all the coordinates and curvatures, and I iterate through all the objects, I'd want to compute the overlap with the winner cells that I stored during training. And the next slide, I'll show you guys a visualization of how computing this overlap even looks like. But are there any questions here? This is very it's a very naive way of doing inference, but it's more like just a sanity check, making sure that one sheet works in this fashion.
I mean, if your goal is to test the algorithm as we published it, and then it seems very straightforward, I guess. Unless I'm missing something.
So this is where the bulk of the information is. Try to go through this one step at a time. So the reason this figure exists is because assume that I've trained on 5 different objects. That's object 5 here, object 6, 7, 8, 9, and 10. And is it too small?
No, starting with 5 is interesting.
Yeah, I just randomly picked somewhere in 5. But the goal here is that I'm inferring on object 7. So I'm seeing object 7, I have no idea what it is. And the only way I can predict what object it could be is by comparing it against previous training data. So if you look at the x-axis for each of these black columns here, the x-axis kind of shows you the winner cells collected during each training observations. So there are about 50 training observations here. In each of them, I've stored a set of winner cells. And on the y-axis, I'm basically looking at my predicted active cells that I collected during each inference observation for this object 7. Again, I have no idea what that object is, but the only way I can predict what that could be is by computing overlap between the winner cells and the predicted active cells. And that's sort of what these dots are inside each of these black columns. It's just the amount of overlap if it's above some certain threshold. So if you look at, let's say, the training observations collected for object 7, and I'm comparing them against the predicted active cells for inference for object 7, I notice that I have the most overlap compared to all these other objects. So you're basically doing, you're trying to pick the object that has the highest total overlap when you're comparing the predicted active cells to the winner cells. That's sort of what you see here. The numbers at the top, they just describe, it's just a sum. It's just what the total overlap is. This is pretty sure that the algorithm thinks with reasonable confidence that what I'm seeing right now is in.
So you're adding these up, but if I had a temporal pooling layer on top of this, I don't have to add anything. It just does it automatically.
Yeah, it does it automatically.
So it's a complex step, but in reality, the neurons would be simple.
Yeah.
But you're showing it visually.
Okay.
Is this right? Who's hit that object?
Yes. Yes. So yeah, it's unknown object 7, but it did predict 7, so that's good. It had a total overlap of about 74. I don't know. The next closest prediction was it could be object 6, which is, I don't know, a total overlap of 26. So it's
So this is over like how many observations?
so 50 training observations and then 50 testing observations. Sorry, 50 training, 50 testing.
Okay. So you might have been able to determine that earlier, right?
I could have, yeah.
Right. You just ran the whole limit and then you said, okay, we're at
29. One issue we have here, which we didn't have in the problems paper, is many of the inference points won't match anything because you're looking at different points you haven't stored. Many of them, despite all the stuff we did, many of them actually don't match at all. So enough match to distinguish it, but so I think it's still an issue here.
the issue being.
Like if you look at object 7,
Yeah.
1, 2, 3, 4, 5, 6, 7, 8 points actually matched. Is that right? Out of 50.
Yeah.
So then, you know, 42 of them didn't match.
Well, it's sort of like saying, well, if I haven't learned the whole object, and now I'm touching on it, and I'm touching points I haven't learned, I can still recognize the object.
Yeah, but if we can recognize it with one grasp,
Yeah.
you know, we have to have a much higher hit rate, I think. I'm not sure we're really solving the continuous.
Okay.
Yeah.
Tried and tested. So yeah, inference is just predicting the object with the highest total overlap between what I collected during testing and what I collected during training. So it's a very simplistic approach, unlike the Collins paper, which has that explicit object ID layer. And the next steps would obviously be to use multiple layers and possibly multiple cortical columns for voting.
Or maybe, as Supervisor just suggested, we might want to really address the continuous representation problem as well. I don't think those two things are just.
Touching in one.
Well, it's a little fuzzy in my mind right now, but the idea that you have very discrete points and very discrete curvatures at every point, and somehow we have to be able to interpolate between. I'm saying you're saying we're not doing that.
We're only doing it within the kind
radius,
of radius of the
within the
thresholds.
radius, right?
Yeah, so in a sense, it addresses, if you say like, you need to sample like 50 points, right, in training. And then, yes, it's shown, it's sort of almost uniform around the object. And if you do that, as long as you pick enough in your test, let's say 25, and so no matter which 25 you put, it's close enough to get.
I think it's okay that many of your sensations do not match anything. What's important is that you eliminate what you do sense eliminates the possibilities, narrows down the choices.
Yeah.
We'll
probably have to change the voting a little bit because nothing matches is not necessarily a bad thing.
Right. Not yet.
Not yet.
Right.
We basically need to loosen up a few things.
It's funny. I have to think of it. It takes some time to think about it. Okay, we're getting close to the results here.
Yeah.
I'm excited.
Okay, so this is sort of what the objects look like.
Really? I didn't even know. So very close. One slide away.
One slide away. Yeah. Okay, so this is what the zoom in. This is really hard to see. Okay, so this is sort of what the training and testing objects could look like. So I've just shown 3 different objects here, and I've showed you the 2 ways I could generate the testing samples from it. In the top row, it's very hard to see the purple points, but the purple points are the training points and the green points are the testing points. So it's a uniform random subsampling of whatever remains outside of my training group that is my testing group. In the bottom row, it's a lot easier to tell because I have these purple points and those are still my training points, but the green ones are occlusions. So it's basically like Karan's example where you take a sheet.
Where the green ones are occlusions or the green ones where you're sampling?
The green ones are both. Those are for testing.
Yeah, but I mean, is that where I'm sampling, testing, or is that like the part I can't see?
That is where you're testing.
Okay,
So that's the part you can't.
that's not the inclusion. This is an included object, and the green points are where you can test.
Correct.
So it
Yeah.
looks like it's 90%.
Yeah, so I was thinking the same thing. You can only touch this part of this object right here, you know.
Well, any more points and the algorithm slows down, so I had to work with
Well, you
what I had.
could,
No, man, you could have a bigger.
you could have fewer green points, but distributed over a large
Yeah,
area.
Yeah, you could say 25% and then, you know, sort of.
I didn't think about doing that.
This is a pretty difficult test, right? You're basically, as he said, as Karan said, you're including 90% of the object, so we'll see how it works. That's a hard standard to meet, I think.
Okay, so the first test is not the occlusions, it's the uniform random subsampling from the testing set. And I'm still using the 13 training objects. I am using 13 training objects. And the goal of this exercise, before I even jump into this graph, is there a sweet spot for the number of training points that I need such that I reach a really high testing accuracy with a limited number of testing samples? That's the question I want answered. So the graph here kind of shows you that test. So all these different lines, they're color coded. They basically describe the same experiment run with a different number of training points or clusters. 20, 50, 100, 150, and 200.
Why did it go down from 150 to 200?
Why did it go down?
Doesn't it look worse?
Oh, the testing accuracy here on the side.
I'm saying, where's the 150 line is lower than the green line, the 100 line. Is that right? Am I reading that right?
Yes, correct. Yeah, you're
And
right.
and the 200 line is lower than the 100 line.
Yeah.
So why would it get worse?
Okay, yeah. So that's the question here.
Okay,
Is
I'm
that-
reading it correctly. Let's
Yes,
put that.
yeah,
All right, keep going.
So the testing accuracy is on the y-axis and the number of test samples that I'm using is on the x-axis. So if you notice something, if you look at the orange and the green lines, which describe 50 and 100 training clusters respectively, the green line is up here and the orange line is right below there. You can see that after about 50 testing samples, it actually reaches 100% accuracy, no matter how many testing samples I use after that. But if I used a little bit more training examples, like 150 or 200, it performs slightly worse. And the reason for that is exactly the intuition behind asking this question. And that is, there is indeed a sweet spot for the number of training clusters I need. Any more than 50 or 100 in this case just introduces noise into the problem.
Well, it's not clear why it introduces noise. These are just additional training points. Why would it make it worse?
Because you're looking at new
So are your radiuses getting smaller?
yeah, your radius is
Oh,
yeah.
oh, okay.
So
Well, that
you're-
explains it. Sure, sure. Right, right.
You're
Now
over-
if I add more training points, now you have to hit them.
Yeah.
Oh,
So
That's interesting.
But that radius is in the clustering algorithm. You're over clustering your training points.
yeah,
I
but
mean, you could have overlapping clusters.
yeah, why would you
could
keep,
have, I
yeah.
mean, you could still have a fixed radius, just allow the clusters to overlap.
Yeah, that's what I
There's
thought you
no-
would have done. So that explains this result, right? The more
Yeah.
you're adding, this now these things getting harder to hit them.
Yeah,
Okay,
I didn't visualize the clusters using like TSNE or something like that. I could have done that, but
it's okay, it's all right.
Yeah.
That explains that result.
How many objects are there?
13.
I would imagine if you kept the radius the same size, then you would have had similar results or better.
Possibly.
Yeah.
Or at least in this limited experiment, the conclusion that we could draw is if you had maybe about 50 to 100 training points and you use greater than 50 testing points, greater than or equal to 50 testing points, you get 100% accurate. So that is all 13 objects are correctly classified.
Yeah, and in some sense, the number of training points if we want to do a continuous representation, the more training you do, it shouldn't lead to, at some point it should stop adding memory. It should stop taking more memory
Yeah.
to do it. And just intuitively, you wouldn't get narrow radiuses here. It's just the point. At some point, since your clusters are overlapping, training a new point doesn't really change anything. You've already learned that space. So that would be like the first thing to do, it seems to me, is like try getting away from that narrowing radiuses here.
I think if I had fixed the radiuses, we probably wouldn't see this. Plus, in addition,
You wouldn't see this.
yeah,
yeah.
it would be good no matter how many training points I used.
Yeah.
But the other thing is that the algorithm needs to have that addition where it doesn't grow segments beyond a certain number of, I guess, like maximum number of segments, right? Because right now I'm continually just adding more and more base.
Right, and that's why you're not really doing continuous learning.
Yeah.
I mean, you're not doing a continuous representation. Because it needs the, if I'm learning the shape of something and I keep moving over it, at some point you just don't learn anything new, right?
And in my case, I am, which is not good, which is not good.
Okay, it's okay, well, we understand that.
Okay, so this is an example, I guess, of where it works. And this is the same example as before. I have 50 training points and 50 testing points. And this is sort of the object that I'm using. And this is like a drill bit or a drill. And if you look, I'm just randomly subsampling my space for my testing points, and those are in green. The other ones, the purple points, are the training points. And over here, you can see that it pretty confidently predicts that object 8, which is this object, is indeed object 8. There's really not much overlap anywhere else. Yeah, That's the one highlighted in red.
I appreciate this is more specific to this situation where it's kind of the object's kind of artificially fixed in an external reference frame. But I'm just curious, like, do you have a sense for how diagnostic the location information itself might be in this case? Just in the sense that, like, there's probably certain regions of the 3D volume that are only sampled by certain objects, and
that's a great question. And I didn't include that in the slides because it didn't work so well. And if you go all the way back,
what didn't work well?
I'll show that in the.
as in just using the location information.
So you're only clustering by locations, basically. I did try this. In this,
as in if your feature essentially is the location, I guess is what I mean.
Yeah.
As in, if you were just to look at the overlap of the feature SDRs with at testing and training and kind of sum across those, if you would get like how many hits you would kind of get, and if that would be enough alone to disambiguate the objects.
Okay, so no basal memory.
Without taking into account curvature. Yeah, exactly. Basically.
It's just proximal input.
Well, I imagine it would be very accurate.
I'm just kind of interested. Yeah, I was just interested in this. Yeah.
It might be, I mean, there's still probably a pretty substantial intersection between different objects, so you'd have to, but you might get some locations that are unique to an object, and then, then you'd be able to
I
recognize it.
don't know if there'd be a lot of substantial overlap. I mean, it's like the two planes of the objects have to be right at the same point. It's like,
Oh, because they're on the surface.
it's not like the occupied volumes, it's the
Oh, the
shared
surface.
surface points,
Oh,
which
it's the
is could
surface.
be pretty low.
How big is the radius compared to the width of the object?
It's 15% of the maximum range of the object. So the range here is 0 to 100. The radius is about 15.
Oh, that's big. So you'd have a fair amount of overlap.
Yeah.
But I think Neil's point's a good one. I think you would be able to recognize objects just by that.
That is a good point.
If we think about this as an exercise entirely to learn continuous representations, then we can dismiss some of these issues because we have, we're assuming we know the locations here. Of course, you have to infer that, right? We don't know that. We assume we know the orientation, but we have to infer that. So all these things we've talked about extensively have to be done. So this is a subset exercise. And as you pointed out about continuous representations and the temporal memory. So as long as we focus on that, and then we can put aside things like Neil just said. Yes, we could be using it, but that's not we're not trying to create a system here that's a practical system. We're trying to exercise a part of it.
Yeah.
I think that's correct.
Yes. Okay. This is a case where it didn't work, and that's if I used too little testing points. So I still have the same 50 training points, the same 13 objects, and I guess the object here is a cup. But I only use 20 testing points. And here there's quite a bit of ambiguity about which object it could be. It could very well be object
It doesn't
10.
look like that. It looks like the object 10 that jumps right out is the least ambiguous. Right?
So it has a higher threshold than all these other ones, but it's incorrect.
Okay, so it's a
it is-
mistake. It's not just ambiguity.
Yeah, I guess it's both, because it thinks, I mean, if you ignore object 10, it could very well be object 6, 7, 9, or 12. They all have about the same
Yeah.
overlap.
But 10 is wrong.
10 is wrong.
Well,
Yeah,
10
it should be 9.
And what is object 10 that it fooled us?
I have no idea. I didn't check.
Okay.
I think it's a dice. It's a deformed dice. It entirely depends on what testing samples I picked here, though.
Well, it shouldn't be entirely dependent on it. It should also be dependent on what the shape of the object is.
It just so happens that the testing samples here most closely match with the training examples of what I collected during the dice.
I understand, but it's not just random which ones you sampled. It's also there's the shape of the object really makes a difference, right?
Yeah.
Should be. I mean, you could, I don't know what the dice looks like. The die looks, I have no idea, but you could imagine if I have a cube in this space, a lot of those points should be similar.
It's both, because what you're describing is parameterized by whatever I trained on, whatever I collected during training. The winner cell is parameterized what the morphology of the object should look like.
Again, I think if we introduce continuously changing locations and curvatures, that you shouldn't get this error.
Okay. This is the second, I guess, subset of testing, and this is not doing that uniform random sampling. This is looking at random occlusions within the testing set. Here, and I didn't vary the number of training points that I needed to use. I used the same as before, so 50 training points, same 13 objects. And the question I want answered here is, how many testing points do I need to get a high enough testing accuracy? And over here on the plot, you can see that I've used quite a reasonable number of testing samples for these occlusions, anywhere from 200 to 800. And what I find is that after about 500 testing points, you get about 100% accuracy.
That's all the 500 in this small.
Yeah, in that small.
I'm surprised you can even get 100% accuracy given how small area you're referring over.
I think it's because I know exactly what curvatures and where the locations are for those curvatures.
If I gave you in that there's a cereal box in that data set and there's a dye in that cereal box and you're just touching on some little surface of it, you wouldn't be able to tell no matter how much you touch. I guess again, unless you're doing what Neil did said, it's the exact location.
That is why.
Yeah.
That is why. Yeah.
Yeah.
So I guess this result seems sort of, I think it makes sense to me, but that's because I know that the locations are completely fixed.
Yeah.
It's a global coordinate system for all the objects. And it's a direct, I can do a one-to-one direct comparison between objects because it's in the exact same coordinate system.
Yeah. So again, all the results have to be interpreted with those limitations.
Yeah, everything should definitely be taken with a grain of salt.
Well, I wouldn't say grain of salt, with those interpretations in mind. It's not random. It's like, okay, given the way you set up the problem, these are the issues that are going to happen.
But in this case, this is like a nice visualization of why it works, I guess. This is like, because it's a screwdriver. It's a weirdly deformed screwdriver.
Oh,
yeah.
That was a real screwdriver.
But the green points are the ones that I can see. And the purple points are the ones that I've trained on. And if you can see here, this is object 11 and it is correctly predicted as object 11 with a huge margin.
But you also did a lot of samples.
I did. There's about 600 samples here, 600 testing samples.
But here, it doesn't seem like you need 600.
I probably don't in this case. That plot I showed earlier was for all 13. Yeah, I need at least 600 or at least 500. This is another case where it works. This is back to that drill. Seeing object date, correctly knows its object date, and it does so with a large margin.
In some sense, seeing so many testing points is similar to kind of running your finger along that green portion of the object, because you get lots and lots of samples.
Well, it is, but yeah, because they're so close together.
Yeah.
It's not continuous, but they're so close together.
You're lifting the finger out of touch.
I guess
In
that's
here, but if you were to just slide along, you'd get probably dozens to hundreds of points.
Even if I represented that continuous movement for the point cloud, I think it implicitly means I am picking it up and touching it, right? There's no like continuous. Okay, this is a case where it didn't work. I have no idea what this object is. This might be a Lego piece. I have no idea.
What?
That's a bag of marbles.
Is this about? I think that was something else.
I don't think you know what Lego pieces look like.
It's 200 testing points instead of 600.
There's so many things going on here. You've got, this very, very small part you're testing, but you are knowing these exact locations again. So
Yeah, and here there is some ambiguity whether this is object 2 or object 11. It should be object 11, but it's predicting it as or no, it should be object 2, but it's predicting it as 11. But, yeah,
or it's not certain. I mean, you can look at that, so it's not certain.
Yeah, if I had a threshold for my prediction, then yeah.
That's a reasonable result given the small subset you're testing, but also all these things we've already talked about means we can't really.
Okay. Open questions, next steps. The first thing I want to address is, I guess, like the downsides of point clouds. And that's something I went over in the beginning, and I want to reiterate it here. And that is, it's very expensive to process. It's very expensive to distill information into salient patches along the surface of any object. And there's this data complexity problem. I don't need like thousands of points to describe exactly what it is.
This is, you're talking about the data set here, right?
Yeah,
this
yeah.
Is, right. This is not, point cloud is not really part of the solution. It's just part of your data set. You're right.
Yes, yeah. So this is like a knock against that particular kind of data set. And where we might want to move forward for more realistic training structures.
But in the real world, we don't start with data in point clouds, right? In the real world, we have objects that we're sensing, and there aren't point clouds. So in some sense, having a point cloud is not it's just a fact of the way the data we're working. And so, getting rid of it is sort of, it's not an important thing other than this practical problem for you, right? I mean, in the end, if you have a real object, you're sensing it, you're not starting with a point cloud.
Yeah.
You're just doing a point cloud because that's what the YCB data set gives you.
Also, some data, actually also YCB, but
Well, I'm saying in a real world, let's say I had some sensor, or even in this day, you could start with this point cloud, but just put aside the pre-processing because that's kind of irrelevant. When you're sampling, you could be calculating those as you sample, right? Couldn't you? Couldn't you be calculating not point clouds, but could you be calculating the SDRs and the?
You could be doing it on the fly, but the reason I did it separately was because it is still very expensive to do it one at a time. It is still quite expensive to do.
Well, you're doing thousands of it up front.
I'm doing thousands up front, but if I just picked one individually, I'm still saying that the process for generating an SDR is still very expensive.
Yeah, but you're only doing 50 of them.
But it's 50, like the 50 most perfect points, basically.
Well,
Like,
50 versus thousands, wouldn't it be less expensive?
imagine like a more realistic training scenario that you pointed out, right?
Yeah.
Where I'm running my finger across that object. I don't know if I could realistically reproduce the same data pre-processing for that more complicated experiment. It would be way too expensive to do that.
I'm not sure why, but I'll take the word for it. And so,
What I'm trying to propose, I guess, is that we should probably move away from point clouds and even
To what?
to more realistic 3D models of objects.
Oh,
Like closest,
like the what, like the facets, what do you call it, the mesh? Like the mesh?
either that or I guess like a I don't know, proper 3D rendered object and the features.
I don't know what a proper 3D rendered object is. I couldn't think of whether any other options.
So I know a couple of weeks ago, Ben was working on a 3D surface reconstruction. So Ben, what was the representation you ended up with there? Was it like a parameterized surface in 3D?
Yeah, it was an implicit function that returns a value greater than greater than 0 when you're outside of the object, and then less than 0 if you're inside the object, and 0 when you're on the object surface.
Let's be clear. I mean, Ben, you've been arguing for parameterized models of objects internal to the system. And here we're just talking about what is the model of the object external to the system that we're using for test data, right? So I just want to make sure that we're not mixing those two up. I guess it doesn't really matter.
Definitely good distinction.
Okay, fine.
I mean, in some sense, I mean, Monty has to work with all of these different data types at some point. I mean, whether it's, I mean, point clouds are kind of like LiDAR data you might get, or, if you were to touch an object multiple times like this, you would get, it's like point clouds with curvature features. I mean, it's not that far from
But
it. It has to work with-
he's processing all these 10,000 plates up front.
Yeah, no, that's a different side, that's a pre-processing
Right,
issue, but in
yeah.
terms of the data format, I think
Yeah.
Monty has to work with point clouds, and it has, or points,
features
3D points, or it has to work with 3D images, it has to work with audio data.
Yeah,
it has to work
right,
with
right.
all of these LiDAR data.
Right.
So at some level.
But that's why, but
it's
you
more about
don't,
the
if
input.
you're training on 50 samples or you're moving your finger, it's not, you shouldn't be doing 10,000 of these things. All right, this is like an engineering problem, not a
Scientific problem.
Yeah.
Someone has a question.
Niels, is that?
Niels?
Sorry, I was just gonna quickly say, it seems like the kind of hierarchy as well that Karan was talking about also last week was would definitely be helpful in terms of just like if you can quickly develop a representation that you are at least looking at a cylinder or a sphere in that kind of fairly or like a reasonably broad region, then that would quickly narrow down the list of objects you need to, and would be kind of a less weird representation than even though you start with a point cloud. But I appreciate implementing that hierarchy is very non-trivial.
Well, you're right, and I didn't hear what Karan presented last week, but we don't want to rely on that right up front. We want to understand the basic mechanisms here because a cylinder is just another object, right? So if we have to limit the number of objects we can learn, well, we have to limit the number of objects we can learn before I have to use a hierarchy. But a single level needs to solve problems and it needs to learn continuously and needs to form continuous representations. So we can introduce hierarchy later, but I think we have to get the basic mechanism working in a single column.
Create continuous representation. Something I've been thinking about this whole meeting is if we have discrete, if we have binary representations.
His radius is that binary? It's not binary.
No, but ultimately the representation that we have in temporal memory is basically an SDR, right?
Yeah, but that's not binary. It's a set of components. Each one is binary, but
Right.
the SDR is not binary.
But it's discrete. You only have finite many possible representations.
Well, it's almost infinite, right? The number of representation you have in SDR is astronomical, right? So it's not limited. I guess the trick is you want representations that are near each other to overlap significantly, right? The representational capacity of an SDR is so it's the trick. You don't want to have a lot of discrete SDR. You want to have overlap between those SDRs. If I'm, the sampling as I move on the surface, I don't want this every point here to be unique. Then you end up with a problem. Does that make sense? Yeah. Am I understanding your point? Maybe I'm mistaken.
I just see it as like you have with SDRs, you have 2 to the power of the dimensionality. That's the maximum number of unique SDRs you can have. So how do you go to continuous representations?
The thing is, there's just so many, right? It's like atoms in the computer, right? There's just so many.
Right. The actual number, the number of ways you can represent, to the sparse is huge. If you have it, the total number of bits is large. It's astronomical. There's no representational problem. The problem is making sure that points that are near each other or similar have similar or overlapping estimates. That's the problem. That's the challenge. It's not a representation capacity problem. It's we don't want to have to. That's what I was getting back to earlier, where both the SDR for the curvature and SDR for the location were highly sparse, which means that in general that would be difficult to have overlap.
Yeah, I guess we briefly addressed hierarchy, but I mean, we don't know if it's needed or not, you said.
Well, it's going to be needed, but I just don't think we should focus on it until we solve the problems with a single column. That would be my recommendation.
Okay.
Right? We have to solve the problems of, hey, you don't know the location, and B, there has to be an overlap for these SDRs, and we don't want to rely just on, we don't want to rely on location to do these things. We want to learn in a way that if I move as if I'm sampling continuously, I think that really makes a difference than if you do sort of random points.
Okay.
I think we have to think about it more.
Ben started this great building brainstorm doc, and I've been contributing to it too. There's a lot of unanswered questions there. I don't know if anyone wants to take a look, whatever. Yeah, that's separate. The other, I guess, next step is can we move away from this fixed object-centric coordinates that I've designed in my system? We should be able to plausibly using grid cell codes. That would enable this sort of actually, I don't know if it enables scale invariance. I don't know why I wrote that, but it should definitely enable viewpoint invariance for sure.
Well, as soon as there's 2 things. One is you can, when you learn an object, you can assume you know its orientation and its location, right? But when you're infer, you don't know those things. And so I think that would be as you say, enable viewpoint. Let's take scale out and rotation invariance, right? Bit cell code, right? I think that would be to me, that would be the higher priority than the hierarchy, okay? Because we haven't really gotten this one layer to work as we want it to work. Is this your last question? I thought the presentation was great.
Thanks, sir.
That was a lot of the illustrations.
Okay, thanks.
Yeah, that's good.